Thank you. Hope all of you are doing good. Um, thanks for that introduction. So let me kick off. So I'll be talking about FP in Scala for big data, an approach to solving a problem that we had when we went to one of our clients. And you've already seen my profile now. So why FP in Scala made difficult? This is a collation of all the reasons and all the comments that I got after talking to a few developers who tried to use Scala for doing their functional programming and for doing their programming in general, and then left off in the middle for a variety of reasons. And this is a collation of those reasons. One thing that they say is they get hit with a ton of jargon. It's not a jargon for us, but it's a jargon for them. So we don't end up communicating properly. And there were a lot of type inference issues when dealing with Scala. Hopefully in Scala 3, that goes away to a great extent. And then type class specializations. Given a problem, we always tend to talk in terms of type classes, and that led to a few communication problem again. And then when we talk about free structures, obviously Scala comes with a whole lot of boilerplate and libraries that handles these boilerplates, and having to know all of them is kind of difficult for a newcomer. And there are many options of solutions. And this all led to slower development of pretty much incomplete or FP in the small. Like you have a scattered set of pure functions, but the overall design is impure. Now, the solution that always tend to work is sticking onto the fundamentals. And it's a hard decision to not use a library and to use a library, So sticking onto fundamentals was the key. Sticking onto referential transparency, we all know that. Total functions, making sure that your functions are handling all of the set of inputs for that type. And lawful abstractions, making use of lawful abstractions kind of takes away the pain of introducing bug in your code. And type-driven development. By the time you move away from that company, you're telling your client or your manager or your colleagues, like if you want to add a new feature or a new change into the code base, the types are going to drive you to do that. Like you don't need to understand the entire piece of code base to make any small change. And the types will help you not do anything funny. And the result is faster development. And that leads to FP in the large. For this problem, first I'll discuss the problem itself, which is a big data problem. The term big data is very relative these days. So we don't really need to focus too much in what exactly is a big data, but the problem comes down to, hey, we have millions and billions of data set transaction records. For example, billions of clickstream events that is hitting your banking app, millions of customer account data set, and then payment data set if it is a bank, and we do business analysis and machine learning. So that's a high level picture, and that's all we need to understand the gist of what I'm trying to talk about. And the problem is finding the attributes of customers. Now, you can take this problem into any level, but if we keep the problem to a minimal surface area, then you can focus on just that surface area and solve that problem nicely. So what that means is I'm not trying to build a library here. I'm not trying to build a product, just an application code base for a client for their specific problem. The problem can be finding the attributes of customers, and the example is total account transaction for each customer in last 3 weeks. And we call these attributes features. I'll be talking about features from now on, feature generation, features. And what we needed was a simple interface to quickly add new features. Now, the first use case was, okay, Afsal, we need a programmatic interface, but we don't want, we want it to be easy. We want to quickly add new features, and we don't want to care about what other features are already existing. All we need was quickly add features and deploy them into production. So we need a thin API to combine them to get a wide table. A wide table means a customer ID and a bunch of features. And we further compose to form tens of hundreds of wide tables. So what does that mean for us? So given that problem, what that means, we need a thin layer of interface where we should be able to declaratively define business logic without the details of performance optimizations. Because you've already added some features that might be features that come along, which is quite similar to the previous features, So you don't really need to care about them, but at the same time, you can't hit the cluster too much, making it less performant. And it should be fairly backend agnostic, because we have had discussions where, which backend engine should we use? So as I said, we are going to reuse some of the open source projects out there to actually run these jobs in the cluster, in the big data space. So we're not building the product, but we are having a thin layer of abstraction on top of it. But at the same time, the question was then, okay, you're building an abstraction. So can I use this abstraction to point to some other backend engine? And the answer should be yes. And we don't have a year to make it happen. Do it quickly. So it's 2 months or 1.5 months. And it's not a prototype. You have to run that in production. A single feature definition for a customer can be as simple as that SQL statement. A customer ID, a sum of credit, and a feature name, which is a sum of credit that happened to the bank account of that customer for the last 14 days from some table, and you're doing the aggregation on top of customer ID, and that's going to be the same. And we have a time associated with that query, and we say that time is mapped to the partition of the data set, and a partition represent an optimized version of querying the data set. Like, if the data is partitioned properly, you get an optimized query. And if you just check the details of that SQL, it's all the logic, which is the aggregation logic, and the name of the feature, and the table, and the time. And we don't want that name, which is sum of credit for the last 14 days. What happens if you have a query that queries last 28 days, but your name is 14 days? And that happened. And so let's fix that. So given that many details, let's express this in Scala. A simple representation would be a feature definition. You have some input data set parameterized by D. Usually we say A and B. Just that some people have got this, it's more, they say it's more readable when you use the first letter of what it represents. And some operation on the data set. Probably the controversial bit in this solution is making use of the expression API exposed by the backend engine. And we don't have the time to build the most complex expression bits here, because otherwise we are rebuilding things like Flink or Dataflow or Beam. So we are not doing it. And we have a name of the feature, and we have the partition, which is a time window, and which can be optional. A simple representation of input is an input can be a constant, or it could be a directory. And you have some helper functions to help out with the type inference, because the type will be inferred as constant in Scala in certain cases, and that will hit your head with a brick often. An example with that representation is feature def, my input, expression, the name of the feature, and the last 14 days, which is a DSL on top of time window. And we can have a list of such features. And apparently this is all that they need. They need a list of feature definitions, and they should be fairly readable. And the expression should be quickly accessible. So here, the account, sum of account balance, you can have some sort of helper functions, not helper functions, combinators within the input structure to join two data sets, and you provide the helper functions there. Now we need to compose them. So given a feature definition, we need to get a representation of the actual feature job. And I'm calling it as a feature gen that returns some sort of feature result that consists of the details of the features included in the result. So essentially, a program that represents feature generation, given some feature definition, right? And the first level, the first level structure of feature gen is that something that is parameterized by a data D, expression A, and some result output A. And you can see things that slowly bridges the gap to functional programming. Now, things like Applicative is slowly coming into picture, but we're not talking about it now. We have a map to function, which takes one feature gen and another feature gen, and a function that goes from A, B to C, and which will allow you to get a job that returns C in return. And we'll see how this is being used. It's very fundamental. It's sticking on to the real fundamentals of FP there. Now, a representation is, you can lift any value to a feature gen job. It's a set of case classes, basically, representing the data. And a zip function takes one feature gen job. It's not a feature, but a feature gen job, another feature gen job, and a map, again, taking a feature gen job on the left and a function that goes from A to B, returning you a feature gen of B, and then a node that says, hey, given some feature definition, how do I create some result out of it? And then join features, probably something that which was not there by the time it was productionized, because it is a specialized version of zip. But the essential difference here is, given a feature gen A and another feature gen that produces A, you join it to give A itself. So it sticks onto the type. And we have some helper functions, which is helping out with type inference. And combine all is a function that takes a non-empty list of feature gen that produces some feature result, and they get reduced to join. So they are all get joined to form the white table. Now, until now, we have never talked about the backend engine. We've already joined some piece of data set. And we have a sequence which takes a list of feature gen job, and that returns a feature gen that is going to return you a list of results. That's going to be really easy, and we made use of the map2 function there to get that. Composing is fairly straightforward now. A job means start the feature job given a definition. You can join all of the jobs together using the join combinator. And using sequence, you can collate all the results and keep it in a list, or you could combine them to form a white table and get the metadata out of it. Okay, so that's simple, right? A single implementation of this feature gen program. Now that we talked about program, now we need to run this to a proper FX system that talks to the outside world, all right? And we need to have only one implementation, which is just, as you would imagine, it takes a feature gen job and recursively call through each node and pipe it to an FX system. We are going to use CO for this. There are other alternatives, lots of alternatives, Monix, Cats.io, with either in it. And I see that Monix has got some bifunctor implementations these days. So we have quite a good bunch of FX systems out there in Scala. And it's a matter of preference at this stage. CO is relatively easy in terms of their concurrency operations, and it's expressive in types because it talks about error and output. And then great type inference. So just a quick introduction. The mental model of CO is, given some input, it either gives you some error E or some result A. And it's a declarative, it's a description of the program, which is not actually not doing any side effects. It's just pure, and you can manipulate this program and then finally trigger it to talk to the outside world. So we're going to use that FX system. Now, as I said, CO takes an input as a context. We are going to say data service is my input, and it produces an error, E, which is app error. You can name it anything, and some result A. So that is our final FX system. And our implementation is given some feature gen job, which is a program that we just discussed, to some analytics task. And we are going to implement this run function, which is going to look at each node. A quick glance into the data service. This is the interface the backend engine is going to implement. And they are all a small subset of functions, like given a feature definition, how do I create a feature? Given some input data set and partition, how do I get the data set? How to do the join? And we'll discuss about project features. Essentially, these are like 12 lines of code when I did with Flink, okay? This is the implementation that takes a feature gen job and converts it to an analytics task, a pure node, and you can lift it to a zip that takes a program on the left and right, and then you recursively call apply function and call the zip of 0, and then map function, which is apply program and map it to F. And join features is applying the left side, zipped with applying on the right side, get the two features, and using the access the environment, which is the data service interface, and then join. And creating the features is essentially the same. You access the environment that knows how to deal with generating the features, and you lift it to the feature result. Now, running this with Flink is quite straightforward. Now, that's a list of feature definitions. It's basically maximum of credit and sum of credit, very simple features. And apparently, most of the features were actually simple in production. Now, let's execute this now. A Flink service, we have an implementation of the data service. Our job is quite simple. We are going to map over the features and start the job and then just combine all. And run is a function that takes a job, which returns here CO. CO takes an environment, so we provide that environment and we get the result that talks to the real world straight away. This is a very complicated execution plan after I ran this with Flink. No point getting into the details, but you can see it's just complex. It's very big. And I couldn't put that into one slide, so I took a video of the execution plan. A simplified version is that. It's a terrible execution plan. I have no idea why Flink behaved like that. And surprisingly, many other backend engines behaved the same. They all have their own optimizers too. So it takes the first join and it waits for the third join waits for the first join to finish. And likewise, there is a sequential outer join. We're not losing any data here, but still it is waiting for the first operations to finish before it combines all of the data set. Now, this is quite terrible when it comes to performance. Now, we hit the first real world issue, and that's sequential outer joins. Now, I'm going to do a small little hack, not at the Flink side or the backend side. Let's look at our program, which is a list of feature gen. I'm going to slide over each of those pairs, and I'm going to call join on each one of them, making sure that you're actually calling the join function on each pair. It's a real hack. But we need to know whether we can solve this problem within our abstraction layer and not at the backend engine. And apparently it worked. You can see it's still terrible, but way better. You can see that's a simplified version of the execution plan where the joins were in parallel. And then finally, the last join was joined with the join 4, which is a join of the first two results. Anyway, you can see all of the join happen in parallel, which means you're saving a time of at least half an hour, maybe for a terabyte of data set, maybe half an hour from 2 hours in EMR. That's what we faced. And we never talked about Flink here. We just talked about only abstractions, even to do that optimization. But that was quite simple. But is that the only thing? We could reduce the number of joins, actually. You can see the join node was a job on the left and a job on the right. What happens if I can get rid of the job on the right and smash it with the job on the left? So we are actually introspecting the program. And to introspect the program, we need to get a summary of the program that we have written. And I'm going to call it as a feature requests. Okay. To begin with, what is a feature request? If you remember, I talked about white table, which is a set of features. So you can think of white table as a collection of Spark data frame or a Flink data frame. Or you can simply talk about it like, oh, it's a map, a Scala map, a map that goes from input and partition to a list of expressions, right? A list of operations on that data set. And merging them is quite simple. You merge the left white table with the right white table. And you know what? That's a monoid addition of map instead of data frame dot join. So everything is, we're talking in terms of abstraction here. Executing them is quite simple. You map over that key value pair, which is the data to the list of expressions. And you call create features node. You could use the helper functions there. And then that's going to return a feature gen job. Now, but that was just one white table, but that's not the summary. A summary could be a list of white tables at the end of the job. And here you go, a set of helper functions to quickly add the new request into the summary. So adding and merging. Merging means you have a list of Y table on the left, a list of Y table on the right, flat map and map over it, and then merge it using the merge function in Y table. Now that's our summary of the program. Now you can go to any sophistication here, but we're sticking on to some simple stuff, which I can explain it to the developers, okay? That is one of the points that I wanted to make here. And now we need to get all the feature requests, which is given a program. Whenever there is a create features, you add it to the request summary. Join means you merge it. Map it means you keep going through the loop. And zip it means you collate it to a list. And that's our optimizer, right? Because we know the summary, you can actually manipulate your program in a better way. So given an existing implementation and given the summary, I should get an optimized implementation. And that's basically, if you have a list of, in your summary, you have a list of Y tables, you map over the Y table. We already know how to execute a Y table that gave you a feature gen. Now you've got all the pre-joined data set, and then you map over each node. So we need to return another function in return, which is the optimized version. Create features doesn't mean you have to create all the features. You can look up. And join features basically means, well, if the create features is not giving any features in return because you've already created those features, join features may or may not have something on the right side. Okay. So join features is apply F1, sit with F2, and you have a either combinator, either in 0, which will push your computations from push the error into the right side of the CO data type. That's basically a detail. Essentially what that means is you may not have something on the left side by the time you join something, and you can simply use pure function to lift it to the feature gen job and use the previous implementation to execute it. That's it. Okay. So a summary would be a feature gen, an existing run implementation, a summary of what we have achieved in the program, call the optimize function which we have implemented. It's not going to be too far from what I have already shown you, like maybe 10 lines of code more than that, although they are details. So that optimize, given the summary, pass a run function, you get an optimized run function, which is returning you a 0, and you provide the Flink service. Okay, so how terrible is this? Let's say still much better. It's still a long one, but still better. But that is a simplified version of the execution plan. We got rid of a whole lot of joins. So from where to where? From here to here. So before was actually an optimized version of a terrible execution plan given by the Flink service, and now it's much better. But are we done yet? You can see that there is no flat map in that program, because flat map needs runtime value to go to the next level of programs. Basically, that means you can't optimize, or you can't get the summary out of the program. So how do we derive features from the features? Well, that is also possible. I'm not getting into the details, but essentially all you need is a project function and a get feature request. All right. So it's building a program that can now take the result of the first level feature gen. Okay. So you can see I'm just going to emit the next program that I need to run to complete the rest of the features, because I could inspect the program. And if I execute that, which is going to be the implementation is going to be almost the same as that of the join optimization that we did. And it's pretty much two. So can I show that in one slide? Yeah, at least I could take this as a screenshot instead of a video. That is one page of execution plan. That's the simplified version of the execution plan. So how much we delve into, we got the abstraction almost right. There are some cutting corners there, but we once we finished up with the abstraction, we could just look at the data, every data nodes, and do all sort of manipulations the way we want. Okay, so here what happened was some of the features were reusing the partitions, and since we were doing a monoidal addition, it made sure that all the list of expressions that operate on a particular partitions was collated together automatically. And that's why I was saying use abstractions whenever possible, and it gives you a lot of advantage. So here, without saying anything like list.foldleft, get all the partitions out there and do a merge, that's not going to be a scalable solution. But one single solution that made sure that all the partitions are together with the help of monoidal map, and you were able to join, you were able to reduce the 5 joins to just one single join. So that's the worst plan, and that's the after, right? So I hope I was able to express the gist of this problem and how did we solve this. We didn't discuss too much about external type classes and things like that, but the fundamentals are necessary. Now, this is not a shortcut to any learning. You have learn. Now, this can be sellable to a client, and they'll be okay with it, because we didn't talk too much about FP there. We didn't talk about loss, by the way. So we said we are able to project features and reuse features. So for example, one law is joining the two projected data set is equal to projecting the joint data set, considering it is an outer join. Okay. So that law will get propagated through to the details of the program, which means propagated through to the Flink service, and make sure that when you join those two data sets, you don't get a runtime exception saying that duplicate feature column. So that law is in terms of abstraction, but nicely get propagated through to the implementation. Make sure that you don't get a runtime exception. I hope you will write test cases for sure. And logging is quite simple. Because all of these are programs which are just data, you could pattern match on each one of them, call some println, and then delegate it to the final implementation. Not a great logging, but for me, that was 1 minute, 2 minute thing to understand what is the execution plan. And is that backend agnostic? Well, all of what I have discussed right now and the optimization just worked with Apache Spark too. And Spark was the one that went into production, maybe because of the type of features that we have built, but for whatever reason, Spark was faster. But it's still comparable. So all of this, it was implemented using Flink because everyone was bored with always using Spark. So we started with Flink, and then because of performance reasons, we moved to Spark as well. There was a lot out there, but that was it. It's sticking on to fundamentals and considering your program as data, introspecting the data for that reason. Still purely functional, introspectable, it's declarative, and you can keep adding new features without having to worry about whether this feature is going to reuse a partition or not. And it all worked with no time spent on boilerplate. Thank you all.